slides. What I have done is grab a few slides from the various presentations here, and I'm going to try to make some points based on other people's slides, things that hit me. In particular, I was asked to do the experimental side of this, but I look at the audience, and the majority of the audience are astrophysicists, data analysts, relativists, and so to do the experimental side would have all of you guys walking out the door so you can get to lunch before the experimenters do. So I'm not really going to do the experimental side. What I'm going to try to do is talk about future detectors and how they interface to the science that you guys want to do, and then try to engage you to tell us what kind of future detectors and future networks do you want. Okay, and let me see if which one is the forward?
Is it on?
Okay.
Yes.
Okay.
If you press this.
Perfect. Okay. So David McClellan showed us this slide that shows what he said were the goals. These are the sensitivity goals for advanced LIGO, Voyager, ET, and Cosmic Explorer. And this is really an important feature of a future detector, how sensitive it is. And notice that each one of these is a major step forward in sensitivity for the future. What that means is greater reach, greater sensitivity, greater signal-to-noise ratio. But what you need also to recognize, look at on something like this is, what's the low-frequency reach? What's the high-frequency reach? Those curves translate into these, the detectable ranges for compact binary systems, for example. Here I'm going to actually tell you that, remember, this is advanced LIGO. We're not actually reaching this, and the reason is because of something that Rana showed you, which is, although those curves that David McClellan showed us were really nice, we don't actually sometimes reach those. And so, for example, here, I believe it's this curve is the actual noise in the interferometer, and this one is what it's supposed to be. And you notice that there's a pretty significant gap at the low frequencies. And sometimes you just can't make things work perfectly the way you think they should on paper, okay? So I'm going to open it up. Anybody have a question about that, a comment?
It says mystery noise.
Yes.
What things have been ruled out, and are there things that are still being explored to explain that mystery noise? Or is it really a mystery? I mean, something similar happened in GEO 600, was never resolved, and people thought that it's of holographic origin. So
yeah, almost every interferometer that's ever been built has had mystery noise, and that mystery noise persists until that detector eventually gets replaced and rebuilt, and then that mystery noise somehow goes away. That particular mystery noise goes away, and a different source of mystery noise appears. And oftentimes, we never know what it is.
But in this case, you don't know.
At this point, we don't know. I also want to point out, we do know some of them. These are the control systems for the angular degrees of freedom on the mirrors and the auxiliary degrees of freedom. And some of those things can be fixed with sufficient work, but it's a lot of work, and it takes the interferometers down when you're working on them. And so you're always making a trade of operating time versus commissioning time. Fred, did you want to?
Yeah, well, partly I'll reinforce the thing you said, but a little more strongly. Every interferometer that's ever operated, and Lisa will do it too, and the pulsar timing people will have similar issues, is always going to have a curve that looks exactly like that, except the only things that ever change are the numbers. Okay, really, I could show you 40-meter data from many years ago, Glasgow 10-meter prototype, they all look like that.
You know, sometimes it's called mystery noise, sometimes it's called glue noise, sometimes it's called, it's all has to do with a noise source that you just don't understand. That if you had infinite resources, you'd always figure it out, but we never do.
Yeah, and in terms of things that have been ruled out, you know, one of the big candidates has been scattering noise. And so there's like an ongoing effort to improve the scattering. We have a few uncontrolled degrees of freedom. So we have a 3-mirror recycling cavity. And one of those mirrors is free to move as it wants to. And when you're in the control room, you can see a flashing light as it swings through. But generally what happens is, what Stan said, is you change the interferometer, and suddenly where the mystery noise was, there's no mystery. But now a little lower in frequency, there's mystery noise of a new type.
Yeah, so I had a question about, you're changing the interferometer, but yeah, this will not be much of a change. Is there anything we know about this mystery noise that is different between the two sites? Are there seasonal variations or anything that we can characterize about it?
There's a lot known about it, but nothing that, you know, nothing that we're going to diagnose here.
Yeah, the sort of thing you get is like, you know, maybe at one site, it's a little bit different, and that's partly because no matter how much you try to make these machines identical, at some level you fail to be identical, because it's in the tolerances of mirror curvatures and how they interact, or you know, the exact placement of a photodiode that might backscatter or something like that.
But I have a question. So has this been seen in Virgo, or has not yet the sensitivity to, you know, to be seen in Virgo?
No, yes, it has been seen in Virgo. Or, yes,
It
Virgo
has
has mystery noise. It's different in character than this, but you know, they have mystery noise too. Okay. They're supposed to be at 16 megaparsecs sensitivity. Right now they're at 45, and it's because of mystery noise.
Yeah, the trend over time with Virgo has been, they also have mystery noise. It typically is cutting in at somewhat higher frequency.
But for example, the statement that Rana made, quite strong, we will never go on the ground below 20 hertz. Is it shared by other experimentalists?
No, I don't think so. Rana might be right, or he might be wrong. We don't, but to make a blanket statement like that is actually an opinion, but, you know. I will point out that mystery noise and the excess noise that we have, for example, the excess control noise we have, almost always occurs at the lowest frequencies, okay? When you look at a curve like this, you see lots of things, but the real crunch comes at these lowest frequencies, where a lot more noise sources contribute, a lot of things that they all gang up right at the lowest frequencies.
One of the hardest things at those frequencies, and a major problem, is we have what in the controls community is called ill-conditioned plant, which is that it's the alignment degrees of freedom of the interferometer are poorly sensed. They're sensed very indirectly, and even though they're very clever sensors. And so figuring out how to do that better may well be, you know, one of the things that help us gain boosts in control noise, but we're kind of locked in to the controls now.
Tarun.
Yeah, if you go back to your previous slide, I just wanted to understand what fraction of the noises, which are the noises that are likely to be site dependent. I mean, when we are setting up LIGO-India, which are the things would be very different experience from what, I mean, one of the things we are relying on is the fact that you have ramped up in sensitivity. We need to do it much faster.
The things that will be different in LIGO-India are, again, going to be predominantly the ones at lowest frequencies, the things called control noise, because they are dependent upon the size of the signals needed to control the orientations of the mirrors and the auxiliary degrees of freedom. The biggest difference that's likely to occur between LIGO-India and the US LIGO sites is the driving forces for angular motions and mirror motions, because the ground noise is going to be somewhat different. And so, since the driving forces are different, the control forces can be reduced or have to be increased, and it will change the noise at the lowest frequency. So the biggest differences between LIGO US and LIGO India are likely to be these things down at the low frequencies. These things up at the high frequencies tend to be laser noise, noise in the electronics, and so on, photodetectors, and those things should be more similar than the things down at the lowest frequencies.
A related question is, in these noises, are they to what extent are they related to the ambient ground noise of, that we are measuring with the seismometers at the ground at low frequencies? How much dependence is there on that?
There's one curve here, I believe it's this one, which is the seismic noise directly coming through and moving the mirror along the degree of freedom that you're measuring. So that one is actually typically not a very significant one. Okay. What the rest of these are, however, is ground motion twisting the mirror and causing angular jitter, perhaps at very low frequencies, less than a hertz, but you have to apply forces to correct for those corrections at low frequencies, at half a hertz, okay? And the correction signal you apply, you filter it so that it's as quiet as possible at higher frequencies, but there are limits to how fast you can roll off the noise and still have a stable servo. And so those things come in here. So they're tricky things to do.
Yeah, if I could just point out though, for an example to answer your question, if you had exactly the same hardware right now operating in LIGO India as Hanford and Livingston, and you had either the Hanford or the Livingston commissioning crew having worked on it, we have an experiment right now. Look at the Hanford and the Livingston ranges. It's 135 megaparsecs at Livingston, and it's 110 at Hanford, and that's because there's an absorbing spot on the ITMX that's about 10 microns on the side. And that makes all the difference, that one absorbing spot.
Yeah.
And that's the kind of difference you can expect. And it takes 6 months of work to figure out that that's your
And by the way, when you look at curves like this and say, well, where is this likely to be right and where is it likely to be wrong? The place where it's most likely to be right is up here, in this region, because that's the part that's dependent upon the high frequency performance of the detectors, and the part that's likely to be most off for the projection are the things over on this side, which are dependent upon the low frequency performance predominantly. So just a guide for reading these things. I'm going to jump forward a little bit. I'm going to grab another slide. This was talking about looking at quarks in the equation possible in neutron stars. Okay, I just grabbed it because it has a pretty illustration, but it points out that there are times when the high frequency performance of these detectors is extremely important. And, we have perhaps concentrated, a bit heavily on the low frequency performance in designing these detectors. Of course, the high frequency improves, but it doesn't improve quite as much as the low frequency performance improves. And so I think if, for example, your big interest in physics is the equation of state of nuclear matter or quasi-normal modes of black holes excited by mergers, and you want to look at the ring downs of those, you need to be pushing very hard on the designers of these instruments for better high-frequency performance. Yeah.
So in bodies like GWIC, has there been a discussion of maybe some groups somewhere should focus on building a better sensitive detector, focusing only at high frequencies, because there are trade-offs, right, between low and high?
I don't think that's ever been discussed, particularly at GWIC, and I don't know that GWIC is even the right venue for something like that. There might be people in the world thinking about high-frequency detectors, possibly in Australia. Different people have kicked around ideas, but I think it's still very early going. But part of this is going to have to come from a user community that really finds interesting science at the high frequency region, because it's not easy to modify those noise curves that I showed you before to improve the high frequency performance. It's possible, but it's not easy, it's not cheap, and somebody's got to make a really compelling science case that it's worth doing. David.
So we're looking at this quite a lot in Australia and at the high frequency detection. And if you look at the slides I put up, there is a slide there showing Osgrav HF and high frequency Voyager. They're now correct in the slides. They weren't when I put them up, but they're now correct. What they do is get you to close to ET and Cosmic Explorer performance at high frequencies. So I understand, are you saying high frequency detectors which exceed even those performances?
Look, I'm just opening this up. I'm just encouraging the people who are interested in these kinds of phenomenon to make a strong case, a strong scientific case about why it's important to do it, because it's possible to make a high-frequency detector that might come online earlier than ET, okay, to probe these problems, or you might be able to make something that's even more sensitive than ET and Cosmic Explorer at those frequencies later on. But it's likely to be kind of it's going to have to be a science-driven case.
And I'll just comment on that as well. This potentially, you could have one of these shorter baseline high-frequency detectors in the early 2030s, which is, could be 10 years before the other interferometers. And you only need one, as long as you have an array of low-frequency detectors.
Yeah, okay. I don't really understand why do you think that no one has made a clear science case? I mean, there is maybe 100 papers starting with exactly that. So if we would see even the length of the ring down signal, that could tell us something. If, let's say, if we could distinguish a hypermassive or a supermassive case, that would restrict the equation of state. If we would even detect an oscillation frequency, that would restrict it even more. So there are connections to short gamma ray burst physics. If we know this thing collapsed or not, so if we could distinguish the magnetar scenario or the the black hole plus disk scenario for that. So there is really too many science cases to enumerate here. So is your comment that they are not specific enough, or what exactly did you miss?
Maybe your community is just too polite and you don't make quite as much noise. That might be part of it. The reason I say that is because, I see the efforts that go into, when the experimenters are designing these things, the efforts that go into making good performance down here, and I don't see them putting the same effort into trying to improve the performance up at that region.
Can I say something? Okay, so I fully agree with him in the sense that in the literature I think there is a very broad and strong, community that is making the case that it's very important to improve the sensitivity at high frequency. In fact, I think for ET and the Cosmic Explorer is one of the science case, if not the most important one, to target the merger of neutron star. It's the main difference between ground-based detector in the future and space-based detector that are not going to do the kind of multi-messenger astronomy we can do with binary neutron stars. So it's really what distinguish, one of the strongest case that distinguish the ground-based and space-based detector, the neutron star, binary neutron star black holes. I wanted to ask a question about this high-frequency detector, which is quite interesting, that you were mentioning. But how is going to be the sensitivity in the low-frequency part of that detector? Because we still would need to measure masses quite well for, even making then statements about equational state. So is it going to improve high frequency, but, degrading sensitivity at low frequency? I don't remember. Maybe you showed the noise curve, but I don't remember.
As I hand it over to I think the idea is that you use the other detectors to measure the masses.
So ideally, the detector is designed such that it has the best sensitivity or comparable to Cosmic Explorer between the range of, say, 900 to 3 kilohertz, and everything below that is better than A+. So you've not lost out completely.
And you achieve this with squeezing, but also signal recycling. Are you narrow band, the high frequency part, to achieve this?
Yeah, so the two ways you can obtain this peak sensitivity is either by detuning your interferometer or making your signal recycling cavity longer. In both cases, you have changed the line width of your signal recycling cavity. And that's how you get this sensitivity. And detuning has other experimental complications, but long signal recycling cavity has slightly more promise because it's more robust to internal losses in the interferometer, which is one of the key things to look out for when you're building an interferometer.
No, I think this is very important.
I think something, at least for me, has been missed in all the discussions of LSC, white papers, and many other things. And what's being missed is they all have the common message that more is better. That's great, right? It's also useless in terms of planning, right? What we really need in terms of planning things, if you do more is better, you're doing exactly what Stan has in the picture up there, okay? And, you're defining things by, when it's going to turn on is defined by funding cycles and all of these things. We're not driving what we're doing with the science, in a sense, because we know we have finite resources, and so we have to make the decisions of what things are more important, and those are generally functions of time as well. And so I was starting this discussion with Archesman after his talk about the fact that, I believe that given capabilities, it's highly likely that the definitive statement on cosmology that can be made with gravitational waves will not be made with neutron star follow-ups, but will be made with binary black holes. And, or at least will first be done. It may best be done eventually by detectors like that and follow-ups if the community in the optical can, manage to be able to deliver the spectra and whatnot. But I think what's really important is when we, as an associate director for observatory operations, when we're making decisions of when we're going to be observing, when are we going to be commissioning, where do we expend the commissioning effort or the instrumentation development and the engineering effort on different things, those are generally functions of time, and they correlate with when satellites go up and when satellites go down, and when new telescopes turn on, like LSST, et cetera. And there's this important dimension of priority and priority versus time that has to become a part of that consideration. Right now, there is none of the literature an argument for a threshold effect. Like, you know, if you don't stop running at this case, you can make this definitive cosmological statement in this particular period of time, whereas if you follow more is better, maybe you make that statement later because you haven't been driving it from the science. And so I think it would be very good if people started to think about the time dimension and the finite resource dimension and say, what are the real priorities to attack and hit first? Because otherwise it's just going to be more is better. People are going to go after the bucket, and that's what's going to determine the development of the future.
I'll just make a very quickly programmatic comment. This is precisely what NSF is asking us to do, to tell what the science goal of A+ or what it is going to do and what will be left for things like Cosmic Explorer and what do you need. Make a trade study, make a very detailed trade study. Why do you need 40 kilometers? Why can't you do it 10 kilometers? What's the frequency range? These are the questions that I agree we have to address and tell the community.
Chris?
So could I just ask you to clarify that issue, that statement about black holes being the things that are going to be predominantly helping us with the cosmology? Just because at the moment that's not the case, and we really are going to be relying on
yes,
the BNS.
but imagine if it turns out that it's extremely hard to follow up binary neutron stars, and you only get for every 4 binary neutron stars only 1 follow-up observation, then it's going to be as bad as binary black holes. Meaning, so in that case, binary black holes might improve.
But
might have the
can
same
I say one thing?
Yeah.
That's true, but it's also true, as Archisman was showing, and as has been shown in paper by Daniel Holz and collaborators. You will not achieve the 1% with binary black holes with the statistical methods at the level, in 2025, because you are going to have this localization in the sky with many galaxies, too many galaxies, and you are not going to reach, you might get 5% or 10%. This is what
but that's
people have
true.
shown.
But binary neutron stars, you may expect at most 25 with advanced LIGO sensitivity per year. It may run for 2 years, so you have 50. With A+, you may get another 50. And let me just continue the argument. You may have 100 sources, out of which, if you have only 25, you don't reach the 1% level that people have been claiming.
Yeah, but what I was trying to say is that whether it is with neutron star, with what you are saying, or black holes, we will not reach few percent.
Correct.
So just
that
to
is
answer so we are not in a good shape at the level of...
I agree with that. Yes, that is what I'm trying to say, that we won't reach, but binary black holes might be equally important in that sense.
Yeah, I think I'd say 50-50 at the moment as to how much contribution each will make, given the uncertainties on all of them.
So again, I pull out this slide and from Arun's talk, where he pointed out that there's a very good chance that we may not see very many binary neutron stars, that they're hard to localize, they're hard to detect, and I think that's something that we need to be working on very hard. I will point out that part of that is this problem of localization, that many of the events that we do have are localized very, very poorly, and so you can't use the large telescopes. There are very few that have decent localization. And again, we get that. This came from Yo's talk, and I'd like to point out that the localization for the LIGO-only detections are very, very poor. They're much improved by adding Virgo. Now, LIGO Virgo is not a very good network. The reason is simply what you see here from, I guess this was Tarun's talk, I just stuffed it in this morning. It doesn't show up very well, but this is the first detection, the localization. It's a big ellipse on the sky. It's determined in, by the separation of the two LIGO detectors, and the two LIGO detectors have continental baselines, but not intercontinental baselines. And so in order to get much better localizations, you really need those intercontinental baselines. And so that brings us back to really needing LIGO-India and CAGRA. CAGRA is frantically trying to get their detector operating right now. We don't know exactly when that's going to happen or exactly what sensitivity they're going to be able to achieve at the moment. But when you look at this, you see the two LIGO detectors are basically almost on top of each other, and they're co-aligned. And so they provide, in some sense, much less than they could provide if they were further apart. There are reasons why they're built the way they were, but that is the motivation for LIGO-India. But it's really, really important that we advocate for this global network. It's not just a matter of, oh, gee, we need to get Cosmic Explorer built in the US because that'll be better, or we just need to get ET going in Europe because that's wonderful and we'll have a lot of fun building it. We really need, from a scientific point of view, the global network, and it's the astrophysicists who have to advocate for that. The experimenters, the people who build the instruments, we really just love building more sensitive instruments. I would be happy to just go and build the most sensitive instrument possible, and I would be as happy as a clam whether there's any astrophysics that comes out of it or not. You guys are the ones who have to advocate for the network. Okay. Did you comment? No, okay. Yo showed this in his talk. I'm not actually going to talk about what he was talking about in terms of the science harvesting. What I really wanted to do is point out that he actually snuck a schedule on in front of you. We'll be observing until mid-2020. We'll turn back on again mid-2021 or late 2021, observe for a year maybe, or a year and a bit, then turn back off again, and then eventually turn back on with the A+, and advanced Virgo plus sensitivities. And I'm just going to ask, what do you guys think about this kind of an observing schedule?
So the green, can you tell the key? The green is data taking?
The green is data taking. Those are observing runs. And the, I don't know, whatever that dark color is commissioning time. Time when the facilities are down, mirrors are being changed, electronics is being changed, all that kind of stuff. Is this something that you're happy with?
So I don't actually, can you clarify? So when A+, I don't understand from the, what is written there. When is supposed A+ to start?
A+ is supposed to be installed in this time frame and operating here.
So after 04, which is supposed to start in 2022,
yeah.
Correct?
Now, none of this is written in concrete. This is all just notional, but I'm interested to know what, so don't start planning your vacations
No.
overlap that.
No, but I wanted to understand for how long 04 is supposed to operate before the installation of
It's
A+.
about 18 months, it looks like.
18 months?
18 months, and with a duty cycle that we are currently seeing, that might mean optimistically 1 year of data.
Well, I think it looks a little less than 18 months, to be honest.
Exactly, yeah.
Yo emphasizes that on this, that that 04 might go longer. The others, maybe there's something else on this slide. He did emphasize that this is still very, very tentative, but that's kind of what people are talking about, maybe a year and a half.
No, that re-emphasizes what I was saying. I was probably being more optimistic. By 2025, we will still only have maybe 10 binary neutron stars with counterparts. A+, yeah, it comes online. We don't know what Virgo is going to be at that level. It says 120 megaparsec there. So it all depends on where we reach, but it is critical to have long observing. I mean, that will also have some commissioning, right? Yo seems to show observing runs beyond 2023 to be continuous. Won't there be breaks beyond that?
I can't imagine that you're going to turn on Advanced Virgo Plus and A Plus at full design sensitivity and run for a long period of time. I'm sure it's going to be turned on at something less than design sensitivity and run for a period of time before you have a commissioning break, okay?
Your question is about a particular aspect or the general timeline?
I don't know. How you guys feel about this? That, you know, only half the time in the next 5 years, there'll actually be gravitational wave detectors.
Yes, so what I was going to say is that we have to be mindful of something that was brought up earlier, that when are the other missions running, like LSST, I think will come up by 2022. It will be good to have a joint observation run for a reasonably long period, right? Because with what Varun mentioned, even when our LIGO detectors or Virgo detectors have sensitivity between 120 to maybe 100, even 60 megaparsec, the limiting magnitudes of these sources will already be challenging, but perhaps LSST can still tap into those.
LSST, I have spoken to people involved in LSST. They're not going to slew the telescope for follow-up of gravitational wave events more than 5% of their telescope time. That means 3 nights, that's it, and 3 gravitational wave events per year. At least that is the plan. In the before 1708-17, that said they will not dedicate any slew time. Now they're saying about 5% of the time because their mission is different. They're not going to slew. So LSST will not be a major follow-up facility of...
we are trying to send more LIGO people to their transient team.
Yeah.
About the schedule, I have a question. What about Virgo and Cagra? So will they synchronize with this, or will they try to cover, I mean, to make things in such a way that there are overlaps all the time?
Well, this is actually the Virgo schedule. It's pretty well coordinated with the LIGO schedule, I believe.
Yeah, we coordinate.
Cagra doesn't have a lot of control, to be honest, of their schedule because they're still in the struggling phase of getting their detector operating for the first time. Once they get it operating, then they know what their sensitivity is, where they need to improve things, and then they'll be able to better schedule. But at the moment, they probably don't have much schedule flexibility, and they also don't have a secure source of funding for the future past the next couple of years. So it's hard for Cagra to know exactly what to do, and so I don't think my guess is they will try to synchronize with this because they probably aren't going to have the same sensitivity as LIGO and Virgo. I could be wrong, but they probably won't. And so therefore, their best bang for the buck, if you will, is to add quality to the parameter estimation of LIGO Virgo. I believe that's what I think that's what they give. That's the biggest bang for the buck, but I don't know. Maybe.
So let's hope that no supernova will explode.
Stan. So personally, I look forward to the gaps. That's when data analysis can relax a little bit and not be in the really exciting mix of everything. And just related to that, the worry is that when new data comes along with big increases in sensitivity, it just goes to another level of challenge for certainly the CBC group having to deal with the higher frequency of events.
Yeah.
But hopefully other groups will be faced with different challenges of finding new signals now. I'd like the focus to switch over to those other groups.
Good. Okay, I just want people to think about this because, in fact, the community, to be honest, for the most part, these schedules are driven by the experimenters, the people who are building the instruments, and they get some input from the astrophysicists, but you guys are having less, I would guess, you're influencing the schedules at about the 10 to 20% level, not the 50% level that probably you ought to be able to influence these schedules.
But can I ask, what is the channel to influence the schedule? Because, we can talk among ourselves, but so how do we do that? Because I don't remember even in the LSE meetings having discussion where people have asked the data analysts, astrophysicists, and theorists to contribute to that decision.
That's what I'm finding out is missing. I don't go to LSE meetings for that reason. The LSE is, I haven't found the LSE meetings useful since about 2015. Because the important science is not being discussed. Okay. The thing that really has to, get started to influence these schedules is we have to move in the gravitational wave community beyond more is better, and also in the astrophysics community, we have to move away from. If you ask them, when do you want this discovered, they tell you as soon as possible. That's not also a useful, actionable comment, okay? Let me give you, for instance, you mentioned 1% on the Hubble constant. That might be a statement about how one can do best. I think, is there new physics likely to be lying in cosmology is a question that needs an answer soonest, not best. Best can come along later, but what is the strategy to be able to say that? Do you need 1% to be able to start to really try to resolve the current tension? Or is it 3%? Those are the kinds of questions you have to ask, because best is, sure, best is best. We'll get there eventually. But it's not the most important thing. The important thing is when can we get there? And think of all the lost opportunity in work of not knowing today, is there new physics there? So I think we have to think about the science differently now and include that time dimension. There has to be a real dialogue between the capabilities and the plans to increase the capabilities, and the plans even to just be observing at a particular time, and the targets.
But the specific question you asked, which was, how do you influence this? You get onto things like the LIGO Program Advisory Committee, and you tell the LIGO director, you need to do this, you need to do that. You get on to, decadal survey committees, which set the priorities for various projects for funding in the US. You get on to corresponding committees in India and in Europe, okay? That's the way that you guys can start to influence those things. There's not a lot we can do more here, so I'm going to jump ahead, but happy to talk later with anyone. See, what else do I have? Oh, this one. This is my favorite, because this is actually the only place I can offer any real science to you. Of course, this is the degeneracy between inclination angle and distance for, and this comes about because we're not measuring the polarization of the waves. If we could measure the polarization of the waves, if we'd had a third detector reasonably optimally located and to get that other polarization, we should be able to limit the inclination angle cosine, the cosine of the inclination angle, to something like plus minus 0.05, I would guess. Okay, I haven't done any numbers, but that's my seat of the pants kind of number. So instead of having this as the range for the inclination angle, you'd actually have something that's about like that. Okay? When you get that good a sensitivity, you can begin to start to test the jet models instead of using the jet models to tell you how far off axis you are. Okay? Questions, comments?
There was a third detector, but it was a matter of sensitivity.
Yeah, there was actually, and and Virgo played an extremely important role in localizing it by not detecting it, which come back and if you want that, but it did play an extremely important role, but not by detecting the other polarization, but by not detecting the signal at all. So that placed the localization, but helped absolutely not at all for the polarization. Okay, and that's again why these intercontinental baselines like LIGO-India, like CAGRA, are so essential for the future of the field. There's something here I'm going to be just slightly well, how much longer do you want? 10 minutes? Okay, then I'll skip this. That's too sensitive. That's okay. Sanjeet put this up, and showing the cosmic stochastic background. And I know the stochastic background people were really excited after we detected the first binary black hole because they realized that that meant that there would soon be a stochastic background for them to detect. Whereas I think they should have been really sad because that stochastic background is going to prevent them from detecting an even more interesting stochastic background. And what we see actually is that, you know, a lot of the detectors, LISA is probably also going to be prevented from getting any place close to inflation by its stochastic background. Maybe the pulsar's timing will do that, but probably they actually have a background from supermassive black holes. This is a place where, gosh, we really need some new good ideas. And finally, I'm going to just flash 2 slides from Suresh's talk. I think he made a really strong case about R&D that should be going on in India, a bunch of areas where future detectors are going to need help. We have curves for these various detectors, ET, Cosmic Explorer, but we actually don't know how to do many of the things that underlie those noise curves. For example, we don't know what coatings to put onto the mirrors because, you know, they picked out a mirror coating made out of unobtainium, and so in the next few years, somebody has to figure out where to mine that and how to apply it for coatings. So there's a lot of really hard work here. This is a place to engage the Indian community. Now, again, I know most of you are astrophysicists or data analysts or machine learning experts, and so you're not going to want to pick up and do work on suspension systems or coatings, but you come from outstanding institutions, you have colleagues in the physics departments who might be experts in material sciences. Go and talk to them, tell them about the exciting challenges of gravitational wave detection, excite them about the work you're doing, and then tell them about the problems that they could contribute to. I think that's really important. Similarly, there are areas in terms of more practical engineering areas, interferometer modeling, interferometer sensing and control, system identification, all of those kinds of things. Very, very important areas, and I encourage you to really go back, look at Suresh's talk, think about whether you have a colleague at your home institution who might be interested in grabbing one of these topics and really getting involved in it. And that's all I have on the experimental side. So I'll throw it open if anybody else, I think Ajith gave me about 7 more minutes, so.
What was your controversial thing you skipped?
One of the things that always strikes me about these curves is how steep the background is falling compared to the signal distribution. So with a tiny change in signal strength, which corresponds to distance, you can go from, the probability of being a noise event is 100 times the probability of being a signal event. And over here, 15% further away, or closer, you have gone a factor of 100 the other way. It's almost certainly, if you detect something with a signal to noise or a ranking statistic of 23 here, it's almost certainly a real event. This curve, noise curve, is falling very, very rapidly. We often talk about how non-Gaussian the noise is in these interferometers, and it is true. There's a lot of funny stuff. But the various techniques that we've used, coincidence, a lot of the vetoing things, have made this really outstandingly a clean data set. And so the take here is that these events right here at the threshold are probably only, I think, marginally worth worrying about. So when I hear somebody talk about doing a sub-threshold comparison between LIGO triggers and sub-threshold GRB triggers, I look at it and say to myself, why in the world would you waste your time doing that? You're going to get another marginally interesting event here, okay? Maybe you'll switch something to be a real event, unless it's got some aspect which is really significantly interesting, like, maybe it's a GRB with a really good location, okay? That might be an interesting thing to compare. But when you're just trying to improve the statistics by finding, improving the threshold 10%, I would just say, why bother? And so for any of you graduate students whose thesis advisor tells you you should go out and try to do those marginal LIGO triggers along with marginal Fermi triggers, just nod your head and find something interesting to do.
So I have similarly mixed feelings about that, but I'll just say the density of points gets higher as you go that way, so there will be more sub-threshold, but they'll be lower quality. So there's this balance between more of something worse, but it can still add to the overall information for population studies and things like that.
Yeah. Anyway, I think it's just, there are lots more interesting things that we could do with our time. If we got, if we've got the time to do it and nobody, you don't have something better to do. But I think there are lots of things that are more interesting. That's what my controversial statement was.
So the effect of using an external data set is more to reduce the look elsewhere effect in terms of time. Because this background is, after you reduce all the non-Gaussian stuff, is basically a chi-square distribution with some number of degrees of freedom, and the look elsewhere effect is given by the number of templates times the overall duration divided by the autocorrelation length of the waveforms, which is very small. So if you, instead of paying the look elsewhere effect of the entire length of the data, if you just have a small list of times, the bar shifts by twice log the the ratio of these things. So that is the value, and not really, I guess, changing the nature of the distribution.
Yeah.
Yeah, actually, maybe I can give a partial answer to your question, why bothering? Well, because other people bother, like the group in Princeton, and they found potentially interesting events, not only just some, they pull out of the noise by making a different, there are differences in their analysis.
And I think what they did was actually very good, the Princeton group. Yeah. If I looked at it, I think they handled the noise estimation in a way that was better than what we did in LIGO. They were also somewhat more aggressive in terms of going for things that were a little bit potentially, a bit iffier. I think within the LSC, we may have been super conservative, and I think the Princeton group was a bit more aggressive. But I think they also did some very smart things in terms of the way they handled the noise and its variability, and I think that may be contributed very much. I'm not an expert by any means, and I think that what they did is very good. And I think if you can do something that's really easy, but when you start to work out MOUs with Fermi and it just looks like a lot of work for
just
not very
wanted to
much
point out that there is at least one interesting candidate they found with very high spin. If it's confirmed, that has a lot of astrophysical consequences to see an element with high spin.
Yeah.
The slide from my talk. Essentially, what I'm trying to say is there are two aspects. In a discussion with Archana earlier today, she essentially asked the same question, and a suggestion that I made was the same. That is, how would we start students and faculty getting interested in this technology? And is there funding for this? So I said two things. One is that we don't have funding right now, but we anticipate funding, let's say optimistically, in a year's time. But we cannot wait for a year because that's too costly. We cannot lose that time, so we have to start working right away. And how would we do that is to enthuse faculty in the institutions who are working in a related field, but look for technological overlaps between what they usually do in their labs and what we need for LIGO. There's a lot of overlap between our regular engineering problems and physics problems and many other laboratories, both in high energy physics, in laser physics, in cold atom physics, in a whole host of, even space industry. So there's a lot of overlapping technologies, which, so they don't need to go out of their way to engage in LIGO-related activities. And I think networking with many such groups would be very beneficial in the next year for the growth of the experimental field.
Right, and the thing I'm trying to advocate for is that the people who are doing the astrophysics, the data analysis for this, should go out and help us identify the people who have expertise, who have experience in related areas, engage them, tell them how interesting gravitational wave detection is and how important their role could be. And I think that's what we really want to do, is engage this audience to help us find a few of those other people to help us do this. And I think I've now spent up all of my time, so thank you very much.